So let's discuss another problem in classical mechanics. So here is the problem. So a heavy chain of uniform mass per unit length is hung from one end. If the mass of the chain is m and length l, the tension at each point of the chain is. So what they are saying is so this is a chain. So a heavy chain of uniform mass per unit length. So the chain is of uniform mass per unit length, just as this. So this is a chain. So like this. So we are having chain of uniform mass per unit length. That means mass is distributed equally. So there is uniform distribution of mass from this end to this end. There is no improper gathering of mass, accumulation of mass like that. So evenly the mass is distributed. So uniform mass per unit length is hung from one end, and if so it is hung from one end. So if the mass of the chain is m and length l, so the mass of this entire chain is capital M and it is of length capital L. So from here to here the length of the chain is capital L and its entire mass, this chain's mass is capital M. The tension at each point of the chain is. So now what we have to find out is what could be the tension at each point. That is, at this point what is the tension of the chain, and at this point what is the tension of the chain, and at this point and at this point what is the tension acting on this chain. That is, at different points what could be the tension. Formula for the tension, that one we need to derive. And where x is the distance from fixed end to any point of the chain. That means suppose this is some certain point on this chain, so x is nothing but distance from, so x is the distance from fixed end to any point on the chain. So this is the fixed end, this end is fixed, this end of the chain. So fixed end, from fixed end to any point on the chain, that is nothing but x, distance from fixed end to any point on the chain. So that is nothing but x. Now we have to find out a formula defining tension at any point on this chain. That is, at this point, at this point, at this point, at this point. It must give us appropriate tension at every point. That one we need to find out. So that is the problem. So understanding the problem is very important first of all. Then we can go to solve the problem. So now the solution for this problem is as follows. So consider a small elementary length dl between the points x plus dx and x. So what we need to consider is here it is shown in this diagram. We need to consider a elementary length dl. So small length dl between the, and it is between the points x plus dx and x. So this is x point and this is x plus dx point. So here length goes on increasing from fixed point to this end. So from here to the from here the tension from this point to any point on the chain, that is nothing but x. So from the here to this point x. So if we go down still more, so that is nothing but x plus dx. That's why we are having here t of x at this point, and this is at this point t of x plus dx, because x goes on increasing as we go from top to bottom. So from here to here x would be L. So it goes on increasing as we move down the length of this chain. So here we have to take any middle part of this chain, some dl elementary length of this chain, some part of this chain at any point. So that is situated at x and x plus dx. So from top to x, from top to x plus dx. So at that distance we need to select a certain mass of the chain. So now what we have to do is We identify the forces acting on the elementary mass contained in the elementary length. So this is elementary length, a small length. See, so this is the overall chain. Here we are taking a little bit of elementary length, little bit of cut. We are just cutting out. We are just imagining. So what would be happening for this elementary length? So we need to identify forces on an elementary mass in elementary length. We draw a free body diagram. So what are all the forces are acting on this elementary length? That one we need to find out. Now, if you see at this point, top point, tension would be acting in upward direction, and here weight of this mass would be acting in downward direction. Delta W is nothing but weight of only this elementary length, only delta W, not the overall change. Delta W is nothing but weight of this elementary chain's length, small part of the chain length. So it would be acting downward, obviously downward. And this is here the tension is acting in downward direction, T of x plus dx. So actually tension comes into the wire because of the weight of the wire. So if we are holding any object, in general case if we think, so we are just actually fighting against the weight of that object. So tension would be acting because of the weight of that object. So if a rope is tied and left like this, here also in the same case. So this is the fixed end, this is the rope. Here this fixed end, it has to hold this entire rope, I mean this entire chain. So this entire chain has certain mass. So because of that mass, weight would be acting vertically downwards. So in order to prevent this chain from falling down because of the gravity, so here at the fixed end, tension has to be supplied in equal amount, equal to weight of this chain. So at this point I'm saying, at this fixed point. So the way in here entire weight of this chain would be acting vertically downwards, weight of this chain. And if that what the tension has to do is it has to overcome this force. That means this weight of the chain must be balanced with this tension. Then only when both the forces are balanced, it would be in equilibrium position. That means it would be at the fixed end. Not only if the weight is greater than tension, what happens means the chain would slip down. So that's why this weight of the chain which is acting in downward direction and the tension which is acting here in the upward direction must be balanced. Then only it would be in appropriately fixed to that end. So in the same manner here also, the tension is acting in downward direction at this point, below point, but here it is acting in upward direction at the point x plus ds. Here tension is acting downward, which means at this point it has to lift the mass of the rope which is lying down. So if this is the rope, if we consider, so here if this is the rope, if we consider at this point, so at this point has to hold the mass of this entire rope which is below this point. So this is the point. So below this point we are having some chain, that is that and this chain has some part of chain, and this part of chain has its own mass. So this point has to hold this entire mass which is lying behind this point, this entire mass of the chain which is lying behind down bottom of this point. So it has to, in this, just as this fixed end holds the mass of this entire chain below at the bottom of it, in the same manner at this point also it has to hold the entire mass of the chain, part of the chain which is lying below this point. So it has to lift this entire mass. So in the same way here also, at below this point, this part is somewhere here, this elementary part is somewhere here. So below this elementary part there would be some part of chain. So that part of chain would be having its own weight, and because of that weight, yeah, it would have tension. So that is the tension here, T of x plus dx. That This tension is because of weight of the chain which is remaining below this elementary mass. So it has to carry out, it has to lift this part of the chain has to lift the entire mass below it. So in lifting it, it would be this bottom part would be having its own weight, and because of that weight, it would be having some tension. So that's why here the arrow is shown in downward direction, because it has to lift that weight as well as and weight of this own elementary mass. So because force of weight of this elementary mass would be acting downwards, and tension because of that lifting that remaining part at the downwards. So that force, these two forces would be acting downwards, and tension would be acting in upward direction because it has to lift the entire thing. Only if this forces in the downward and the forces in the upward directions, when both of them are balanced, then only the chain would be in equilibrium position. Otherwise it would be keeping on elongating if the weight is more than, if tension is less than weight. So when balancing of this upward and downward direction forces takes place, then only the chain would remain fixed to the fixed end without any change. So that is the forces acting on this elementary mass. So now consider a small elementary length dl between the points expressed here. So that one we have considered a free body. So from the free body diagram, from this diagram, t of x is acting in upward direction, and this has to be balanced with downward direction forces, that is delta w plus t of x plus dx. So t of x plus dx delta w, that is delta x. So now t of x delta w, that is mass of this part of the chain, this elementary length, that is given as this. So actually what is the mass of the entire rope? Mg. So this entire rope's mass is weight is mg, and it is of length L. So mass per unit length. So how much unit length? So if we take suppose the rope is of 10 centimeter, like that if you take, and its mass is 50 grams. So for each centimeter how much we will get? 50 grams by 10, that is 5 grams. So length of each centimeter of this chain is 5 grams, that is 50 grams by 10 centimeter, that is mass per unit length. So how much for unit length here is 1 centimeter. Each centimeter, if 10 centimeter of the chain weighs 50 grams, then how much 1 centimeter of that chain weights is nothing but 5 grams. That is because that is nothing but mass per unit length, that is nothing but m by L. So m is entire mass of the chain and L is entire length of the chain. So mass per unit length that you would get, and mg, if you multiply it with g, that is nothing but weight is mg. So mass per unit length into g, so weight acting on unit length of the rope. But here the length of this chain is dx. We are taking dx elementary length of the chain, so we need to find only weight of this much length of the rope. So what we would do is we just multiply. So here weight for unit length of the rope multiplied with length of the elementary length of the rope, that gives the weight of this part of the rope, this elementary length dx of the rope. So hence we need to so that's why we are having mg by L dx. And next is here, this is t of x plus delta x. So we have from Taylor's series expansion, we have a formula, that is f of x plus h, that is nothing but f of x plus h into f dash of x. So actually f of x plus h is equals to f of x plus h into f dash of x. This is the formula from Taylor's series. So this is the formula, f of x plus h is equals to f of x plus h into f dash of x. So this is the formula from Taylor's series expansion. We are having this formula. So based on this formula, f of x plus h, f of x plus h into f dash of x, here also same, t of x plus delta x, in the place of f we are having t, and x and h in the place of h delta x. So that's why t of x plus h, that is nothing but delta x into f dash of x is nothing but t dt by dx. So that's why we are having this formula. Now what we have to do is just simplify it. So t of x here, t of x here would get cancelled, and this mg dx by l we have to send to that side. So here it is adding, so on going to that side it would subtract. So here also this is nothing but dx, delta x is nothing but dx. So dx would get cancelled. It is common here. So if we cancel this one here, 0 would be remaining. So here dx, here also dx. So if you take common, so what would be remaining is mg by l plus dt by dx. So if we send this mg by l to that side, so that is nothing but dt by dx is equals to minus mg by l. Now what we have to do is integrating on both sides. So just send this dx this side and just start integrating on both sides. So integration of dt is nothing but t, and integration of minus mg by l x dx is nothing but, here mg by l is a constant, mass of the rope chain, mass of the chain and length of the chain is constant, and g acceleration due to gravity, that is also constant. So if it would be taken, we have to take it aside. So integration of integration of dx is nothing but x, and this is a constant of integration. Here we are having minus, so that minus. So here where a is where a is a constant of integration, so had x is equals to l, t equals to 0. So when x is equals to l, t is 0, that means at the length of the rope. So here x is nothing but distance from fixed end to any point on the rope. So actually what they have given, the length, entire length of the rope is L. So until here we would be having L, x is equals to L from here to here. So at x is equals to L, this point, it does not need to lift any mass because there is no mass below this point. So it does not need to lift any mass. So if it does not need to lift any mass, means there is no tension. Tension would be 0 at this point. At this point of the rope, at this end, there is no mass below this point. When there is mass below the point, then only we will get some tension, some force, some weight because of that weight. Here there is no mass below this point, hence tension would be 0. So that's why at x is equals to L, t is 0. So this condition we need to substitute in this equation. So at x is equals to L, here L would get cancelled, t equals 0. So a is nothing but mg. So a is mg. So in this equation we have to substitute in the place of a mg. So here t is nothing but minus mgx by L plus mg. Here mg into L by L we need to divide by, here we are having only mg. A is nothing but mg from this calculation. If we substitute in this equation, this calculation, L would get cancelled, t is 0 and a is equals to plus mg if this goes that side. So in the we have found out a value from this condition. So that value we need to substitute in this main equation. So mg we substitute. Here mgx by L is there, here only mg. So into L by L we need to do. So after doing that, mgl, if you take mgl common, here mg here we are having mgx by L minus mgx by L. Here we would have mgl by L. So if you take that mg by L common, what we remaining is, here L would be there and here minus x. So L minus x. So finally we would have this. After doing calculation, after substituting value of a in this equation from this condition, we would find out the value of a. If we substitute in this equation, after simplification we would have this. So by taking mg by L common, so here L would be remaining, here minus x. So L minus x. So this is the tension formula for tension at each point on the rope. So for example, suppose if you consider x is 0. If x is 0, what would happen? So if x is 0, L minus 0, L would get cancelled, t is mg. So the t is at this point. So at this point x would be 0. At this point x is L. At this point x would be 0. So at this point it has to carry the entire chain, this point. Entire mass of the chain, it has to hold this entire mass of the chain. So that because of that, it would be having tension. So this entire because of this entire mass, it would be having weight, that is nothing but capital Mg. So hence in this formula, if you substitute x equals to 0, what you would get is LL would cancel, T is Mg. So tension is equal to Mg at this fixed chain. So that is because of mass. Mass would be acting in downward direction and tension would act in opposite direction, that is in upward direction, in order to hold the rope. Otherwise the rope would fall. So that is the problem and its solution. So thank you.